Okay, let's dive right into this. When you got out of bed this morning, or, walked across the room to grab your coffee, you probably didn't give a second thought to the absolute mechanical and neurological miracle that just happened. Walking feels so simple, right? So automatic. But beneath that simple act of putting one foot in front of the other, there is a staggering symphony of signals bouncing between your spine, your brainstem, and your cerebral cortex. So, today in this explainer, we're going to unpack the fascinating science of human locomotion. We're relying on the comprehensive research of Dr. Roger J. Elbow to take a really brilliant systems-based approach. We'll look at some beautifully detailed diagrams to see exactly how we walk, and, maybe more importantly, what happens when specific parts of that incredibly complex system break down. To do that, we've got a very clear roadmap for our explainer today. We'll start with the anatomy of locomotion and the normal gait cycle. Then, we'll build our way up the neurological ladder, looking at lowest level, middle level, and highest level gait disorders, before we wrap the whole thing up with some fascinating key clinical gait profiles.
All right, moving right along to Section 1, the anatomy of locomotion.
So, walking doesn't just happen in the brain. It's a full-body network. At the very base, down in your spine, you have the spinal cord central pattern generator. Think of this as the metronome. It generates your basic rhythmic stepping motion. Moving up, the brainstem and cerebellum act as the great coordinators. They use sensory feedback to keep your posture and balance dialed in real time. Then we hit the midbrain locomotor region, which is basically the ignition switch that actually initiates your gait. Finally, at the very top, the executive suite, the frontal cortex and the basal ganglia. This is your highest level control, letting you adapt to your environment, step around obstacles, and consciously direct your movements. All of these interconnected systems absolutely have to work in perfect harmony to safely transition your body from standing still to moving forward.
Okay, Section 2, the normal gait cycle. Let's look at what happens when all those neural pathways are firing exactly right.
Just look at the seamless progression in this beautiful diagram, from the moment the heel strikes the floor to the moment it leaves again. It is incredibly fluid. One complete gait cycle actually consists of two distinct steps, which we call a stride. You can really see that elegant transfer of weight and the rhythmic oscillation of the body as it moves forward.
The truly crucial thing to understand here is that this cycle is meticulously optimized for energy efficiency. We break it down into 4 precise phases. First, double limb support, where both feet are on the ground. That's only about 10% of the cycle. Next is the first single limb support while one leg swings forward. Then, a second double limb support as that swinging foot lands. And finally, the second single limb support as the other leg swings. During this whole sequence, your total body's center of mass is oscillating vertically and horizontally, and your body is naturally trying to minimize those excursions to expend the absolute least amount of energy possible. It's brilliant. This is exactly why any disruption to this cycle, any abnormality at all, usually causes a massive spike in the energy required just to take a single step.
That brings us to Section 3, lowest level gait disorders. We're going to use the classic Nutt, Marsden, and Thompson classification scheme here, starting right at the foundation.
Lowest level gait disorders essentially represent mechanical or structural faults in the machinery itself. We're talking about disturbances originating completely outside the central command systems. This means diseases of the muscles, the peripheral nerves, the skeleton, or even the peripheral vestibular and visual systems. Oh, and it also includes really common non-neurologic stuff like severe arthritis or just secondary muscle deconditioning from inactivity. When we map out these lowest level disorders, their characteristics are super predictable. For example, if the muscular system is compromised in the hip girdle, you're going to see a myopathic or waddling gait, shifting weight heavily from side to side. If peripheral nerves fail and cause bilateral foot drop, you get a steppage gait. That's where the patient has to lift their knees artificially high just to clear their toes, almost like an exaggerated march. And if the joints are damaged, you'll see an arthritic or antalgic gait, which is basically just a distinctive limp to avoid pain. The big takeaway here, these specific gaits don't really change based on the patient's emotional state or environment. The mechanical limitation is fixed.
Okay, on to Section 4, middle level gait disorders. What happens when we ascend the neurological ladder and the transmission pathways themselves are compromised? Middle-level disorders happen when the brain and spine are basically struggling to communicate. We're talking about lesions in the ascending and descending sensory motor tracts, or damage to the cerebellar pathways. This is where you start to see spastic, choreic, or ataxic gaits. Imagine really erratic, unpredictable limb movements.
A spastic gait might look like stiff, scissoring legs. Choriate gaits involve these involuntary, almost dance-like twitches. And an ataxic gait, it's wide-based and reeling. It's literally like watching someone try to walk on the deck of a ship in a storm, because the feedback loops that regulate rhythm are fundamentally broken. The gait gets deeply dysrhythmic, but it still stems from pathway damage, not a total failure of executive intent.
Which brings us to Section 5, Highest-Level Gait Disorders. Now we're in the executive command center, where the highest cognitive and motor loops fail.
Now, there is a totally critical distinction here. Lowest and middle-level disorders are mechanically predictable, right? Highest-level disorders are a completely different animal because the pathology sits up in the cortical, basal ganglia, thalamocortical loops, the actual parts of the brain that adapt our walking to our surroundings. The resulting gait is totally bizarre. It's highly variable and deeply influenced by environment, emotion, and transitional movements, like starting, stopping, or turning. You literally can't just examine these patients while they're sitting down. Their deficits usually only pop up when they try to interact with complex environments.
And these traits can be absolutely baffling to caregivers. Take absent rescue reactions, for instance. If a healthy person trips, a dozen automatic reflexes fire instantly to throw a hand out or take a quick step to catch their balance. Patients with highest-level disorders, they might lose this entirely. If they lose balance, they might make zero attempt to catch themselves, quite literally falling like a log. Or their brain sends the wrong signal entirely, making them push backward when they're just trying to stand up from a chair. They might even freeze completely when facing a tiny obstacle like a doorway threshold. It's this unpredictable, environmentally triggered chaos that shows a complete breakdown in the brain's highest adaptive controls.
All right, last up, Section 6, Key Clinical Gait Profiles. Let's see how all this anatomy and pathology translates into actual clinical diagnoses.
First up is the cautious gait. To really get this, I want you to imagine how you walk when you have to navigate a patch of really slippery ice. You slow way down. You widen your stance. You keep your feet on the floor longer, shorten your stride, and you barely swing your arms, right? That universal guarded movement is exactly what a cautious gait looks like. It's a non-specific compensatory response. Patients adopt this pattern really early on when dealing with all sorts of mild neurological impairments, and it can actually mask the more specific diagnostic signs of whatever underlying disease they might have.
But we can beautifully map these bizarre clinical symptoms right back to their precise pathological origins. Look at how start hesitation and freezing trace right back to the frontal lobes and basal ganglia. Parkinsonian gait, with those characteristic short, shuffling steps, is heavily rooted in basal ganglia dysfunction. A reeling, ataxic gait points squarely at the cerebellum or the spinocerebellar tracts. The exact nature of the stride is basically a clinical roadmap directly into the central nervous system.
Now, akinetic gait, or freezing, is a truly fascinating anomaly. A patient's legs might move perfectly fine when they're seated, but the second they stand up to walk, it's like their feet are just glued to the floor. But, and here's the crazy part, those frozen pathways can sometimes be tricked into action. If a doctor puts an inverted cane on the floor right in front of the patient to give them a clear visual target, they will often just effortlessly step right over it and start walking normally. The visual cue literally bypasses the damaged internal pathways, letting a completely different part of the brain jumpstart the gait cycle. It is a real game changer.
Another totally stunning clinical profile is pusher syndrome, which is a form of central disequilibrium. This usually happens after a stroke in the posterior thalamus, and patients suffer from a profound illusion regarding gravity. They literally perceive their body orientation to be tilted. So astonishingly, they will actively use their healthy, unaffected limbs to mistakenly push themselves toward their paralyzed side. They're unknowingly sabotaging their own stability because their brain is feeding them a completely distorted reality.
Honestly, this whole topic just brilliantly illustrates how much we take for granted every single day. From the simple rhythmic generators down in our spine, all the way up to the highest executive loops in our frontal lobes, an absolutely flawless chain of command is required to execute just a single normal stride. So I'll leave you with this final thought. The next time you take a step, will you notice the invisible command center keeping you on your feet? Thank you for exploring the miraculous architecture of human walking with us today.